Picture this, you're standing under a clear night sky, gazing up at the shimmering stars scattered across the vastness. But what if I told you that right above us lies one of the most enigmatic and inexplicable realms in the universe? A colossal cosmic home, not just to billions of stars like our sun, but to black holes that devour light, invisible forces shaping galaxies, and signals from the depths of space that defy explanation. The Milky Way is more than just a collection of stars. It is a treasure chest of mysteries that continue to stump even the brightest scientific minds. In this video, we're peeling back the layers to explore 25 of the most baffling and awe-inspiring phenomena hiding within our galaxy. From invisible matter controlling the cosmos to stars moving so fast they could escape the gravitational pull of the galaxy entirely. Each of these mysteries pulls us another step closer to understanding the universe and ourselves. So get ready to journey into the heart of the unknown as we unravel secrets that will make you see the Milky Way in ways you never imagined. Keep watching, because the deeper we look, the stranger things get. Now turning to one of the most enigmatic and fearsome features of our galaxy, let's meet the Great Annihilator, a name that truly captures its ominous nature. This massive black hole, located near the galactic center, has fascinated and puzzled astronomers for decades. What sets the Great Annihilator apart is its remarkable release of high-energy gamma rays, an invisible yet incredibly powerful form of radiation. These gamma rays, bursting with energy, have left scientists scratching their heads, questioning how and why such emissions occur. One prevailing theory suggests that the Great Annihilator might actually be a binary system, meaning it could involve not just the black hole itself, but also a massive companion star orbiting close by. If this is the case, the intense gravitational forces between the two could be creating the perfect conditions for matter to spiral into the black hole, generating these extraordinary gamma-ray bursts. What makes this phenomenon even more intriguing is the scale of destruction and transformation happening in this cosmic dance. The Great Annihilator offers us a front-row seat to some of the universe's most extreme physics, yet its true nature remains a puzzle scientists are eager to solve. And if you think black holes like this are extraordinary, just wait, there are even more celestial mysteries ahead in our journey through the Milky Way. As the next chapter in our cosmic exploration unfolds, we encounter one of the most perplexing and elusive phenomena in the universe, the dark matter halo. To understand this mysterious entity, let's first clarify what dark matter is, or rather, what it isn't. Dark matter is not the kind of matter we see, touch, or interact with in our daily lives. It neither emits nor absorbs light, making it completely invisible to telescopes and other instruments that rely on detecting electromagnetic radiation. Yet, despite its invisibility, scientists believe dark matter makes up a staggering 85% of the universe's total matter. Surrounding the Milky Way like an enormous, unseen cocoon, the dark matter halo exerts a powerful gravitational influence, literally holding the galaxy together and affecting the motion of its stars. Imagine tracing the movement of stars through the galaxy, only to find that their speeds defy all expectations based on the visible matter alone. This is where dark matter comes into play. It serves as the missing ingredient in the equations, explaining why stars at the outer edges of the galaxy are moving far faster than they should be, given the gravitational pull of visible material. Despite its critical role, scientists are still grappling with the challenge of detecting dark matter directly. Numerous experiments around the world are attempting to capture even the faintest evidence of its existence, from observing its gravitational effects on galaxy formations to using highly sensitive underground detectors that may one day reveal dark matter particles. So far, its true nature remains one of the greatest scientific puzzles. Some theorists speculate that dark matter could be composed of exotic particles that interact with regular matter only through gravity, while others suggest it might be a clue pointing to entirely new physics. The dark matter halo surrounding our galaxy not only holds the Milky Way together, but also teases us with secrets that could fundamentally reshape our understanding of the universe. And as we unravel one mystery, it opens the door to many more. Stay with us as we continue to uncover the hidden wonders of our galaxy. Now turning to a phenomenon that feels like a message from the cosmos itself, we delve into fast radio bursts, those enigmatic, high-energy radio pulses that flash across the universe in mere milliseconds. Imagine a burst of energy so powerful that it outshines the entire galaxy for a fraction of a second, and then silence. These bursts were first discovered in 2007, and ever since, they've left scientists scratching their heads trying to decipher their source and meaning. What makes fast radio bursts so intriguing is not just their fleeting nature, but also the sheer distance they travel. Many originate from galaxies billions of light years away, defying easy explanation. But here's where it gets even more mysterious. A recurring fast radio burst was detected within our own Milky Way, the first of its kind. This discovery was monumental, as it allowed scientists to trace the phenomenon to a known source, a type of highly magnetized neutron star called a magnetar. Magnetars are already extraordinary objects with magnetic fields trillions of times stronger than Earth's, capable of generating bursts of energy under extreme conditions. But here's the kicker: not all fast radio bursts fit neatly into this explanation. Some appear to come from environments vastly different from where we'd expect magnetars to exist, while others show patterns and signals that seem almost intentional. Could these bursts be the cosmic equivalent of Morse code, sent by some advanced civilization? Or are they natural phenomena we simply don't yet understand? Despite years of research, the exact mechanism behind these bursts remains a cosmic mystery, with potential implications for astrophysics, cosmology, and even the search for extraterrestrial life. The more we learn, the more questions arise, drawing us deeper into the puzzle. And speaking of mysteries that challenge the limits of our understanding, let's move on to another fascinating marvel of the Milky Way that offers a glimpse into its explosive past. Now turning to the next cosmic enigma, we encounter the Fermi Bubbles, colossal gamma ray, emitting structures that stretch above and below the center of the Milky Way. Discovered in 2010 using the Fermi Gamma Ray Space Telescope, these massive bubbles span an astonishing 25,000 light-years each, dwarfing our solar system in scale. But what makes them truly captivating is their mysterious origin. One leading theory suggests these bubbles are remnants of explosive activity from Sagittarius A star, the supermassive black hole at the heart of our galaxy. If true, they might be the lingering echoes of an ancient outburst that occurred millions of years ago, offering a rare glimpse into an event that dramatically shaped the Milky Way. Another intriguing hypothesis proposes that these bubbles could be the result of an intense wave of star formation, where the births and deaths of countless massive stars ejected energy and matter on an unfathomable scale. The gamma rays emitted by the Fermi bubbles hold clues to their origin, revealing patterns that scientists are still deciphering. What adds even more to the mystery is their sharp edges, a feature that hints at a powerful and sudden event rather than a gradual process. Yet, despite all the data gathered, their true nature remains elusive, leaving experts to wonder what secrets these enigmatic structures might still hold. Could they be telling us a story of the Milky Way's turbulent past, or are they pointing to phenomena we have yet to comprehend? Whatever the case, the Fermi bubbles are a humbling reminder of the vast forces at work in our galaxy. With questions swirling around their formation and significance, let's dive deeper into the heart of the Milky Way to uncover a region even more extreme and enigmatic. Moving forward, we find ourselves venturing into the very heart of the Milky Way, an area astronomers often refer to as the Galactic Core. This region is not just the geographical center of our galaxy, but also a cosmic crucible of unrelenting activity and extreme conditions. Dominating the galactic core is Sagittarius A star, a supermassive black hole with a mass 4 million times greater than that of our Sun. Despite its immense size and gravitational pull, this enigmatic black hole is surprisingly quiet compared to others of its kind, only occasionally emitting mysterious flares of energy that leave scientists puzzling over their cause. Surrounding Sagittarius A star is a dense and chaotic collection of stars, gas, and dust, orbiting in an intricate dance under its massive gravitational influence. This environment is so extreme that studying it is a monumental challenge, even with the most advanced telescopes. However, what makes the galactic core truly fascinating is how much we have yet to learn about it. For instance, scientists are still uncertain why some stars in this area zip through space at breakneck speeds, reaching velocities of thousands of miles per second, while others appear almost stationary. Could these speeding stars have been slingshot by the immense gravity of Sagittarius A star, or is there another enigmatic force at play? The chaotic surroundings of the galactic core also hide secrets about the formation and evolution of galaxies. By peering into this incredible region, researchers hope to uncover insights into how the Milky Way came to be and how galaxies like ours evolve over time. Yet, despite all our efforts, the galactic core remains shrouded in mystery, a region so densely packed and turbulent that it often defies observation. It is this veil of the unknown that makes the center of our galaxy one of the most tantalizing areas of study in the entire universe. As we leave this forbidden zone brimming with unanswered questions, our journey continues to a phenomenon that defies the natural order of life and death in the cosmos. With the next phase of the journey in sight, let us explore one of the most bizarre and fascinating phenomena in the cosmos: zombie stars. Imagine a star that has seemingly met its end, a faint white dwarf no longer capable of generating energy through fusion. Yet, rather than fading quietly into the void, these stars find a way to defy their cosmic fate. By siphoning material from a nearby companion star, they reignite with a burst of energy, seemingly returning from the dead, a trait that has earned them their haunting nickname. As they draw in matter, these zombie stars grow denser and hotter until they reach a critical threshold. At this point, the reanimated star can explode in a spectacular supernova, one of the most powerful and luminous events in the universe. These explosions are not just awe-inspiring displays of cosmic power, they play a crucial role in our understanding of the universe itself. The consistent brightness of these supernovae, known as Type 1 a supernova, allows scientists to use them as cosmic mile markers, measuring vast distances across the universe and even shedding light on the rate of its expansion. Without these rogue celestial entities, our understanding of the cosmos would be far less complete. But how these white dwarfs manage to pull off such a dramatic transformation remains a topic of intense study. Are there specific conditions that make a white dwarf capable of revival? Or could there be aspects of stellar evolution we have yet to grasp? These questions drive astronomers to keep a close watch on these so-called zombie stars, as each new discovery provides a puzzle piece that helps us better understand the life cycles of stars and the fundamental forces shaping the universe. As we leave these cosmic survivors behind, the universe presents us with yet another extraordinary tale, one written in the colossal collisions that define the very structure of our galaxy. With the next phase of the journey in sight, we now delve into one of the most dramatic and far-reaching phenomena in the Milky Way's history: galactic cannibalism. Picture galaxies as colossal celestial entities, each containing billions of stars, gas clouds, and dark matter moving through the vastness of space. When two galaxies cross paths, their gravitational forces engage in a cosmic tug-of-war, leading to an extraordinary event where the larger galaxy begins to absorb the smaller one. The Milky Way, our home galaxy, has grown and evolved over billions of years by consuming smaller galaxies in this manner. Among its many cosmic meals, one of the most significant is the ongoing consumption of the Sagittarius dwarf galaxy. Discovered relatively recently, this smaller galaxy is being stretched and torn apart by the immense gravitational pull of the Milky Way. The remnants of this galactic collision can still be seen today in streams of stars that loop around our galaxy like celestial fingerprints of a colossal event. These mergers are not just destructive, they are also immensely creative. The influx of stars, gas, and other materials from the smaller galaxy fuels star formation in the larger galaxy, giving rise to new stellar generations. At the same time, the gravitational interactions reshape the structure of the Milky Way, influencing everything from the galaxy's spiral arms to the distribution of dark matter. Yet, questions remain about the specifics of these collisions. How many smaller galaxies has the Milky Way devoured over its lifetime, and what role does galactic cannibalism play in shaping the universe's architecture? Scientists continue to study the remnants of past collisions, such as stellar streams and unique star clusters, to uncover clues about these massive cosmic events. Each discovery adds another layer to our understanding of how galaxies grow, evolve, and interact. As the echoes of these galactic feasts ripple through the cosmos, they remind us of the dynamic and ever-changing nature of our universe. Now turning to another cosmic enigma, let us explore the perplexing mystery of the missing satellites, a puzzle that challenges our very theories of galaxy formation. Now turning to the perplexing missing satellites problem, we encounter a mystery that has baffled astronomers for decades. According to computer simulations of galaxy formation, the Milky Way should be surrounded by hundreds, if not thousands, of smaller satellite galaxies. Yet, when we look at the sky, we observe only a small fraction of these predicted satellite galaxies. This stark discrepancy between theory and observation raises profound questions about our understanding of the cosmos. Why are so many of these galaxies missing, or could they be present but concealed from our view? Some scientists believe that many of these satellites might be simply too faint to detect, composed mainly of dark matter with very few stars to give away their presence. Dark matter, the enigmatic substance that makes up most of the universe's mass, does not emit light, making it effectively invisible except through its gravitational influence. These invisible satellite galaxies could exist, but they remain elusive in our current observations. Others suggest that our galaxy's past interactions, including collisions with other galaxies, might have stripped away or absorbed these smaller satellites entirely, leaving behind little evidence of their existence. Another possibility is that our models of galaxy formation need revision. Perhaps the processes that govern how stars and galaxies form include unknown factors that lead to fewer visible satellites than expected. Exploring this puzzle has pushed scientists to develop new technologies, such as more sensitive telescopes and innovative data analysis methods. These advancements have already revealed previously undetected faint galaxies, offering hope that many more are waiting to be uncovered. Yet the question remains, are we missing the satellites themselves, or is there a more profound flaw in the models we use to understand our galaxy's structure? The missing satellites problem not only challenges our knowledge of the Milky Way, but also touches on the very building blocks of cosmic architecture. As we continue our search for answers, this enigma reminds us of just how much remains hidden in the vast expanse of the universe. Moving forward, let us turn our attention to another lesser-known aspect of our galaxy, the starburst ring, a hidden factory of stars near the galactic center that has more than a few surprises of its own. With the next phase of the journey in sight, we delve into the enigmatic starburst ring, a celestial wonder hiding near the galactic center. This region, often overshadowed by the chaos of the Milky Way's bustling core, is a dynamic factory of star formation. The starburst ring is an area teeming with activity, where the conditions are just right for stars to be born at an extraordinary rate. What makes this region even more fascinating is the immense energy it generates. Massive clouds of gas and dust collide under intense gravitational forces, triggering bursts of star formation that far exceed the norm seen in common areas of the galaxy. As young, hot stars ignite within these clusters, their powerful radiation and stellar winds create a turbulent environment, shaping the surrounding matter with immense force. Oddly enough, despite being so close to the galactic center, the starburst ring had remained relatively unnoticed for years. Its discovery challenged the assumption that star formation slows down near galactic cores, where conditions are typically more chaotic. Instead, the starburst ring defies this expectation, showcasing a prolific level of activity that has drawn the attention of astronomers. What fuels this exceptional activity is still an ongoing puzzle. Some theories suggest that the supermassive black hole at the galactic center, known as Sagittarius A, may indirectly influence the starburst ring by driving gravitational waves that compress the surrounding gas into dense pockets, ideal conditions for star formation. Others point to the possibility of past galactic collisions or interactions funneling vast amounts of material into this zone, sparking the ring's rapid growth and activity. Even more compelling is the possibility that the starburst ring holds clues about how galaxies evolve and sustain their stellar populations over billions of years. By studying its extraordinary dynamics, astronomers aim to understand not only the processes driving star formation, but also the life cycles of gas and dust in active parts of the galaxy. The intense radiation emitted by the ring also provides a unique window into high-energy phenomena, including the interaction of young stars with their chaotic surroundings. As our technology advances, more discoveries in this vibrant region are bound to emerge, offering us new perspectives on the inner workings of our galaxy. From an overlooked region to a key focus of scientific inquiry, the starburst ring exemplifies how much is left to uncover within the Milky Way, but our journey doesn't stop here. Next, we set our sights on yet another startling revelation, the discovery of exoplanets in the densely packed galactic bulge, a region long thought to be inhospitable to such planetary formations. Now turning to the densely packed heart of the Milky Way, we encounter one of the most unexpected discoveries in recent years: exoplanets in the galactic bulge. The galactic bulge, a tightly concentrated region of ancient stars near the center of our galaxy, was long thought to be an unlikely place for planets to exist, let alone thrive. This puzzling assumption stemmed from the extreme conditions within the bulge. Intense radiation, powerful gravitational forces, and frequent stellar collisions create an environment that seems far too hostile for the delicate processes required to form and sustain planets. Yet, against all odds, astronomers have uncovered evidence of planets quietly orbiting stars amid this cosmic turbulence. So why is this such a groundbreaking revelation? It challenges some of the foundational ideas we held about how and where planets form. The traditional view suggested that stable, less chaotic regions like the spiral arms where our own solar system resides would be the primary cradles for planetary formation. The galactic bulge's dense and volatile nature seemed to exclude it from this narrative. However, the discovery of exoplanets here forces scientists to reconsider these assumptions. It reveals that planetary formation might be more adaptable and robust than we ever imagined, capable of occurring even in the most tumultuous of settings. Adding to the intrigue, these exoplanets could potentially unlock deeper secrets about the early stages of planetary evolution. Since the stars in the galactic bulge are some of the oldest in the Milky Way, any associated planets may hold clues about conditions in the galaxy's distant past. This could help scientists piece together the timeline of how planets formed not just in common regions like our solar neighborhood, but across a much wider range of environments. Furthermore, this discovery raises exciting questions about the sheer diversity of planetary systems. By comparing these bulge-based exoplanets with those found in quieter regions, researchers may uncover patterns or surprising anomalies that deepen our understanding of how planets and their host stars interact. Even more fascinating is the possibility that these planets could harbor unique attributes shaped by the intense conditions of the galactic bulge. Could they have developed unusual compositions due to the abundance of certain elements in this star-rich region? Could their atmospheres, if they exist, provide insights into how planets adapt to high radiation environments? The answers to these questions are still out of reach, but they underscore just how much this discovery has expanded the scope of planetary science. As technology improves and observational techniques advance, we may soon uncover more planetary secrets hidden within the galactic bulge. This discovery not only broadens our understanding of where planets can form, but also sparks the imagination about the diverse and often surprising ways our galaxy continues to evolve. But the surprises don't end there. As we continue our journey through the Milky Way, we next unravel the story of hypervelocity stars, stellar wanderers traveling at speeds so immense that they may escape the galaxy entirely. Now turning to the phenomenon of hypervelocity stars, we delve into the cosmic mystery of these extraordinary wanderers. These stars, racing through space at speeds so astonishing that they could potentially escape the gravitational pull of the Milky Way, have left astronomers both fascinated and puzzled. To put their velocity into perspective, consider that these stars are moving hundreds of times faster than our Sun orbits the center of the galaxy. But what could propel them to such astonishing speeds? The most widely accepted explanation points to interactions with Sagittarius A*, the supermassive black hole at the core of our galaxy. When a binary star system ventures too close to this black hole, the intense gravitational forces can tear the pair apart, flinging one star outward at unimaginable speeds while the other is often consumed or trapped in orbit around the black hole. This dramatic process essentially turns one star into a high-velocity exile, sent hurtling through the cosmos. However, Sagittarius A* is not the only potential culprit. Hypervelocity stars may also result from galactic collisions or the chaotic dynamics within dense star clusters. For example, during a close encounter with multiple massive stars, gravitational interactions could accelerate a star to hypervelocity status, ejecting it from its home environment. These runaway stars offer a unique glimpse into the violent and dynamic processes that shape our galaxy. They act as tracers, revealing the hidden gravitational forces at play and shedding light on the otherwise invisible structures of the Milky Way. What makes hypervelocity stars even more intriguing is that they might carry with them vital clues about the regions they've left behind. By studying their chemical composition, astronomers can infer details about the environment these stars originated from. Were they born in the galactic core, surrounded by ancient metal-rich stars, or do they hail from a far more distant and perhaps less understood region of the galaxy? The answers could not only help us map the Milky Way structure, but also refine our understanding of how stars interact with the extreme forces in their surroundings. Interestingly, hypervelocity stars also challenge our understanding of galactic boundaries. If these stars escape the gravitational pull of the Milky Way entirely, they become part of intergalactic space. What happens to a star in this vast, near-empty void? Does its trajectory remain stable, or could it eventually interact with other galaxies? These questions push the boundaries of what we know about stellar dynamics and the life cycle of stars beyond their home galaxies. As astronomers continue to identify and study hypervelocity stars, new observations may reveal entirely unexpected patterns or origins. Advances in telescopes and space missions capable of tracking stellar motions with incredible precision will undoubtedly fuel discoveries that reshape our understanding of these interstellar sprinters. And as we continue to explore the Milky Way's many mysteries, we find that its wonders only multiply. Moving forward, let us turn our attention to a phenomenon that offers glimpses into hidden treasures within our galaxy, the fleeting and fascinating microlensing events. With the next phase of the journey in sight, we arrive at the captivating world of microlensing events, often described as the galaxy's game of cosmic peekaboo. These extraordinary occurrences take place when a massive object, like a star or planet, passes directly in front of a more distant star from our line of sight. As this alignment occurs, the gravity of the foreground object acts as a lens, bending and magnifying the light from the background star. The result is a sudden and temporary brightening of the star, a fleeting signal that something unseen has briefly made its presence known. What makes microlensing so remarkable is its ability to unveil hidden celestial objects, revealing entities that might otherwise remain invisible. Rogue planets, which are planets drifting through space unattached to any star, are one of the most exciting discoveries made possible through microlensing. These wandering worlds are notoriously difficult to detect, as they emit no light of their own and can only be identified when they create these brief, bright flashes. Even more intriguingly, microlensing events have sparked discussions about the possible presence of dark matter candidates, helping scientists probe the mysterious, invisible substance that permeates the universe. However, capturing microlensing events is no simple task. These occurrences are not only rare but also unpredictable, lasting anywhere from just a few hours to several days. This means astronomers must constantly monitor vast portions of the sky, relying on advanced telescopes and sophisticated algorithms to detect these fleeting moments amidst the vast cosmic expanse. It is a challenge that demands both precision and persistence, but the rewards are immense. Every microlensing event offers a unique opportunity to glimpse hidden objects and phenomena that would otherwise evade detection, providing valuable insights into the complexities of our galaxy. Beyond their role in revealing hidden celestial bodies, microlensing events have also transformed how we study the structure of the Milky Way. By analyzing these occurrences, astronomers can map out the distribution of stars, planets, and other massive objects throughout the galaxy, piecing together a more complete picture of its intricate architecture. Furthermore, studying microlensing events near the galactic core or in densely packed star clusters can shed light on environments that are otherwise challenging to observe due to their intense brightness or density. As technology advances, the field of microlensing is set to flourish even further. Upcoming space missions and next-generation telescopes will enhance our ability to monitor the sky with unparalleled precision, increasing the likelihood of capturing these elusive events. With each new discovery, microlensing continues to illuminate the hidden corners of our galaxy, proving that even the briefest moments can hold profound cosmic secrets. And as we turn our gaze from these transient wonders, we move into yet another mystery of the Milky Way, a strange absence that defies our expectations, known as the Kepler gap. Now turning to one of the more puzzling phenomena revealed by modern astronomy, we encounter what scientists call the Kepler gap, a baffling mystery that emerged from data gathered by the groundbreaking Kepler Space Telescope. This gap refers to the peculiar absence of planets in certain orbital ranges around stars, a void that stands out in contrast to the otherwise diverse distribution of planetary systems found across the Milky Way. At first glance, it might appear to be a simple artifact of our detection methods, a limitation of the way we search for distant worlds. After all, the transit method used by Kepler, which observes a planet passing in front of its host star, requires precise conditions to detect a planet. Could it be that these missing planets are merely hidden from our view, their orbits not conveniently aligned with our instruments, or is there something far more profound at play here? What makes the Kepler gap so intriguing is its potential to challenge our understanding of how planetary systems form. Planetary formation is a process shaped by the chaotic interplay of gravity, gas, and dust within protoplanetary disks, environments that surround young stars. The absence of planets in these specific regions could suggest that these orbital zones are unstable, preventing planets from forming or persisting over cosmic timescales. Alternatively, gravitational forces exerted by larger, neighboring planets might have disrupted the orbits of smaller worlds, either ejecting them from their systems entirely or preventing them from settling into these gaps. This mystery has led astronomers to consider whether the Kepler gap might hint at variations in the compositions or dynamics of protoplanetary disks across the galaxy. Could factors like the distribution of heavy elements, magnetic fields, or even the type of host star play a role in creating these planetary deserts? Or is it possible that we are witnessing the remnants of past cataclysmic events, such as planetary migrations or collisions, that have sculpted certain systems into their current gap-filled states? As researchers strive to answer these questions, the Kepler gap serves as a reminder of how much remains unknown about our galaxy. Continued advancements in exoplanet detection, coupled with innovative approaches to analyzing planetary systems, offer hope for uncovering the secrets behind this enigmatic phenomenon. And as we explore these gaps in our understanding, we prepare to shift our focus once more, diving into the strange and remarkable world of high-velocity clouds, galactic nomads that roam the Milky Way with an energy and purpose yet to be fully understood. With the next phase of the journey in sight, we encounter an enigma that drifts through the Milky Way like restless wanderers, high-velocity clouds. These immense collections of gas moving at astonishing speeds have puzzled astronomers for decades. Unlike the more predictable motions of the galaxy's stars and well-known gas clouds, these galactic nomads travel with velocities so extreme that they defy easy explanation. What are they and where did they come from? These are questions that continue to challenge our understanding of the Milky Way's dynamic and ever-changing nature. One theory suggests that high-velocity clouds might be remnants of ancient galaxies, long since consumed by the Milky Way's gravitational appetite. As our galaxy grew by merging with smaller neighbors over billions of years, it likely stripped these galaxies of their gas, flinging it into chaotic, high-speed orbits. These clouds could thus serve as fossils of cosmic history, preserving clues about the Milky Way's violent and turbulent past. Another possibility is that they are the result of ongoing galactic collisions or interactions. When galaxies or large structures of gas pass near each other, gravitational forces can create powerful disturbances, ejecting material that races across space in unpredictable directions. Adding to the mystery, some high-velocity clouds show chemical compositions that differ markedly from the gas found within the Milky Way. This raises questions about whether they originated outside our galaxy entirely, potentially arriving as intergalactic wanderers, material from beyond the Milky Way that has been captured by its gravity. Alternatively, some scientists propose that these clouds might be part of a process called galactic fountain activity. In this cycle, massive explosions from supernova in the galactic disk propel gas into the halo of the galaxy, where it cools and eventually falls back in, creating high-speed streams as it descends. Despite decades of study, high-velocity clouds remain poorly understood, partly due to the challenge of observing them. They are often faint and difficult to detect, requiring sensitive instruments capable of studying their motion and composition across vast distances. However, these elusive structures hold the potential to illuminate key aspects of our galaxy's evolution, offering answers about how material flows within and around the Milky Way. As scientists work to unravel their secrets, these galactic nomads remind us of the restless energy that defines the cosmos, always in motion, always shifting. And as our understanding of these high-speed travelers grows, another question arises: what else might be lurking in the shadows of our galaxy, waiting to surprise us? With that thought, we turn our attention to the enigmatic X-ray binaries, cosmic systems where the mysteries of gravitational extremes take center stage. Now turning to the enigmatic realm of X-ray binaries, we delve into a phenomenon often dubbed the cosmic vampires of the Milky Way. These fascinating systems consist of a neutron star or a black hole locked in a gravitational dance with a companion star. What makes X-ray binaries so extraordinary is their macabre process of siphoning matter from their stellar partner. This stolen material forms a swirling disk of gas around the dense object, a process called accretion. And in this extreme environment, the gas is heated to millions of degrees, emitting powerful X-rays that can be detected across vast cosmic distances. The behavior of X-ray binaries serves as a natural laboratory for understanding some of the most extreme physical conditions in the universe. For instance, their intense gravitational fields allow scientists to study how matter behaves as it spirals toward a point of no return, providing crucial insights into the nature of neutron stars and black holes. These systems also help us probe one of the most mysterious phenomena in the universe: how black holes grow and evolve over time. One particularly intriguing aspect of X-ray binaries is their variability. Some systems flare up dramatically, releasing bursts of X-rays in unpredictable patterns. This behavior often results from instabilities in the accretion disk, where matter doesn't flow smoothly, but instead builds up and releases in sudden, dramatic episodes. Observing these flares helps to refine our understanding of how energy is released through accretion and sheds light on the complex dynamics near these compact objects. Interestingly, not all X-ray binaries are created equal. Some are bright and short-lived, displaying their dramatic energy output over a timescale of mere millions of years, which is brief in cosmic terms. Others are quieter, evolving over billions of years, offering a long-term view of how these systems develop. Moreover, their distribution across the Milky Way reveals another layer of mystery. Many are found near the galactic center, where stars are densely packed, but others appear in quieter, more isolated regions, challenging our ideas about how and where such systems form. X-ray binaries not only act as cosmic beacons to detect black holes and neutron stars, but also play a pivotal role in helping scientists measure distances within and beyond our galaxy. By analyzing their X-ray emissions, astronomers can determine critical parameters like mass, spin, and even the chemical makeup of the surrounding environment. This data enriches our broader understanding of galactic dynamics and the behavior of matter under extreme conditions. As we continue to uncover the secrets of these celestial vampires, they remind us of the constant interplay of creation and destruction that defines the cosmos. Just as X-ray binaries represent the immense power of gravitational forces, they also bring us one step closer to unraveling the mysteries of black holes and the fundamental laws that govern our universe. And as new observations bring these systems into sharper focus, our journey through the mysteries of the Milky Way takes another exciting turn. Up next, we uncover the peculiar odd radio circles, a mystery that has only recently begun to unfold, offering yet another glimpse into the unexplained phenomena that define our galaxy. Now turning to the newest mystery in the cosmic catalog, odd radio circles have emerged as one of the most perplexing phenomena in recent astronomical discoveries. These peculiar, faint, circular structures of radio waves were first identified just a few years ago, catching scientists completely off guard. Their sheer size is staggering, spanning millions of light years across, yet they emit no visible light, making them incredibly elusive. Most of these odd radio circles appear to reside far beyond the Milky Way, deep in the extragalactic wilderness, but intriguingly, one potential candidate might lie within our galaxy. This raises a tantalizing question: what could possibly create such an enormous and enigmatic radio structure? Scientists have proposed several potential explanations, but none fully resolve the mystery. Some suggest that odd radio circles could be the aftermath of colossal explosions, perhaps the remnants of massive galactic events like the merger of supermassive black holes or the explosive endings of gigantic stars. Others hypothesize that they might result from intense jets of energy emitted by active galactic nuclei, leaving behind these ghostly imprints in space. However, none of these ideas completely account for their unusual shape, scale, and uniformity. Adding to the enigma is the fact that odd radio circles seem to exist in complete isolation, unlinked to any observable galaxies or stellar activity. If the one potential odd radio circle within the Milky Way is confirmed, it could revolutionize our understanding of these phenomena. Its proximity would allow astronomers to probe its structure and composition in greater detail, possibly uncovering clues about their origins. Are they connected to the mysterious magnetic fields that weave through the galaxy? Could they involve phenomena we have yet to comprehend? The answers remain tantalizingly out of reach, driving scientists to study these strange entities with ever more advanced telescopes. Odd radio circles also highlight the sheer scale of what remains unexplored in the cosmos. They remind us that even in an age of sophisticated instruments and vast astronomical datasets, the universe continues to surprise us with the unexpected. With each discovery, these enigmatic circles challenge our assumptions and push the boundaries of what we know about galaxies, space, and time. As the investigation into odd radio circles unfolds, it promises to uncover new layers of cosmic complexity, sparking fresh questions about the fundamental forces at play in the universe. Moving forward, our journey into the Milky Way dives into the puzzling problem of galactic rotation curves, a conundrum that led to one of the most groundbreaking theories in modern astronomy. Moving forward, the problem of galactic rotation curves presents one of the most profound puzzles in modern astrophysics. At the heart of this mystery lies the way stars move within galaxies, including our very own Milky Way. Based on what we can see, stars, gas, and other visible matter, the outer regions of galaxies should rotate more slowly than the inner regions. This expectation stems from the basic laws of gravity, where objects farther from the center should feel weaker gravitational forces. And yet, observations reveal a completely different reality. Stars in the outer edges of galaxies, far from the dense central regions, are moving at speeds that defy these predictions. Instead of slowing down, they maintain nearly constant velocities, as though influenced by some invisible force. This puzzling discrepancy between observed rotational speeds and theoretical predictions has given rise to one of the most compelling ideas in modern astronomy: the existence of dark matter. Dark matter refers to a mysterious, unseen substance that doesn't emit, absorb, or reflect light, making it completely invisible. Yet, its gravitational effects seem to permeate galaxies, forming a vast halo that influences the motion of stars and gas. The theory suggests that dark matter provides the extra gravitational pull needed to account for the unexpectedly high rotational speeds in the outer regions of galaxies. Scientists have developed numerous experiments and models to understand the nature of dark matter, but so far it has remained elusive. It does not seem to interact with regular matter in any way other than through gravity, and despite state-of-the-art detection methods, no definitive evidence for its composition has been found. Some astrophysicists propose that dark matter could be made up of exotic particles unlike anything we encounter in everyday life, while others explore alternative explanations, such as modifications to the laws of gravity themselves. The problem of galactic rotation curves serves as a powerful reminder of how much we have yet to learn about the universe. It pushes the boundaries of human curiosity, urging scientists to question fundamental assumptions and seek answers to some of the most profound cosmic mysteries. Could dark matter hold the key, or are we on the verge of a revolutionary breakthrough that might rewrite the rules of physics? While we ponder these questions, the journey continues as we delve into the ancient, enigmatic formations known as globular clusters, each carrying secrets about the Milky Way's distant past. Now turning to the mysterious globular clusters, these ancient and densely packed star clusters orbit the Milky Way like cosmic sentinels, holding secrets from the galaxy's distant past. Each globular cluster contains hundreds of thousands, sometimes millions, of stars bound tightly together by gravity. What makes these formations fascinating is not just their age, often dating back more than 10 billion years, but also their enigmatic behavior and origins. Their orbits around the Milky Way are anything but uniform. While some follow predictable paths, others have highly unusual trajectories, almost chaotic, as if they've been tossed around by past galactic interactions. This unpredictable movement hints at a violent history, possibly involving the Milky Way's cannibalistic past when it merged with or devoured smaller galaxies to grow into its current size. Many researchers believe that some globular clusters may actually be the remnants of these devoured galaxies, serving as ancient fossils that preserve fragments of galactic cores. By studying their chemical composition, scientists have discovered that certain clusters contain heavier elements, suggesting they formed in environments richer in metals, likely within other galaxies, before being captured by the Milky Way's gravitational pull. Meanwhile, others appear astonishingly pristine, providing unique insights into the conditions of the early universe when the first stars and galaxies were just beginning to form. Globular clusters also challenge current theories of galactic evolution. For instance, their formation remains a subject of debate. How did so many stars end up so densely packed, and why do they remain so stable over billions of years? Some clusters exhibit unexpected patterns in their star populations, hinting at processes that defy existing models of star formation. Additionally, their extreme densities raise questions about the presence of black holes and other exotic objects at their cores. Could these clusters harbor unseen forces that influence their dynamics, or are we missing a critical piece of the puzzle? As we unravel the mysteries of globular clusters, they continue to illuminate the Milky Way story in ways we never imagined. Each cluster is a time capsule, offering glimpses into the turbulent and transformative events that shaped our galaxy. And so, our exploration of the Milky Way's enigmas persists, leading us next to a strange and frigid anomaly known as the cold spot, a phenomenon that might redefine how we understand the structure of our universe. As the next phase of the journey comes into focus, we encounter the cold spot, a chilling anomaly that has puzzled astronomers for decades. Found in the cosmic microwave background, the faint afterglow of the universe's birth, this region is significantly cooler than its surroundings. While the difference in temperature might seem minor, it stands out enough to raise profound questions about the structure of the universe and the role our galaxy plays in it. Could this cold spot be the result of a massive void, an area of space almost completely devoid of galaxies, stars, and even the mysterious dark matter? Or does it whisper of something even more extraordinary, perhaps a phenomenon beyond our current understanding of physics? Some argue that the cold spot may indeed align with a vast cosmic void, a region so empty of matter that light traveling through it loses energy, creating the illusion of colder temperatures. If this is the case, the discovery may reshape how we perceive the distribution of matter across the cosmos, revealing places where the universe is far less uniform than we once believed. However, this explanation doesn't sit well with everyone. Alternative theories suggest that the cold spot might be linked to the early universe itself, possibly the result of quantum fluctuations in the moments following the Big Bang. Such an origin would make it a direct clue to the very mechanisms that forged the cosmos we see today. Intriguingly, there are also more speculative ideas in play. Some researchers have proposed that the cold spot could be evidence of an interaction between our universe and another, hinting at the existence of parallel universes. Though these ideas remain highly theoretical, they add an extra layer of mystery to an already perplexing enigma. Whatever the cause, the cold spot represents a challenge to our understanding of the universe's composition and the forces that have shaped it since the dawn of time. As we strive to decode this frigid riddle, the cold spot reminds us that the Milky Way is not just a participant in the cosmic dance, but also a stage where unfathomable phenomena unfold. Each discovery brings us closer to unraveling the grand tapestry of existence, bridging gaps between the known and the unknown. With this in mind, our journey now leads us to the wandering wanderers of our galaxy, the rogue planet's celestial bodies adrift in the vastness of space, unbound by the warmth of a host star. With the next phase of the journey in sight, we now turn to the rogue planets, the lonely wanderers of the Milky Way. These celestial nomads drift through the galaxy, untethered to any host star. Unlike the planets familiar to us, which orbit stars in predictable paths, rogue planets travel the cosmos in solitude, unbound by the gravitational pull of a stellar companion. But how do these fascinating drifters come to exist? Scientists believe that rogue planets are often born like traditional planets, forming within the swirling disks of gas and dust surrounding young stars. However, some are cast out of their systems by gravitational interactions or collisions, flung into the vast emptiness of space where they continue their journey alone. Others may form independently, coalescing directly from interstellar material without ever being tied to a star. What makes these wandering worlds particularly intriguing is their sheer abundance. Researchers suggest that rogue planets may outnumber the stars themselves, populating the galaxy in astonishing numbers. Advanced detection methods, including gravitational microlensing, have provided glimpses of these elusive objects, revealing a hidden population that challenges our understanding of planetary systems. Despite their isolation, rogue planets hold tantalizing possibilities for hosting life. Some may retain internal heat generated by radioactive decay or gravitational compression, creating subsurface environments where life could potentially thrive even in the absence of sunlight. Others may carry icy oceans concealed beneath thick crusts, preserving conditions that could support microbial life. These mysterious travelers remind us of the boundless diversity within the Milky Way and the many secrets it still holds. Each rogue planet is a story of cosmic evolution, a fragment of the galaxy's history drifting silently through the void. As we continue to search for these elusive worlds, they offer not only the promise of new discoveries, but also a deeper understanding of how planets form and evolve. Now, as we leave behind these solitary wanderers, we turn our attention to the most powerful explosions in the universe, the awe-inspiring gamma-ray bursts that occasionally light up the Milky Way with their unparalleled brilliance. Now turning to the ultimate cosmic fireworks, gamma-ray bursts stand as the most energetic explosions known in the universe. These phenomenal events unleash more energy in a matter of seconds than our Sun will produce over its entire lifetime. Some of these astonishing bursts have been traced back to the Milky Way, though their exact origins often remain shrouded in mystery. So, what could possibly power such colossal blasts? Scientists suggest several potential sources, with one leading contender being the dramatic collision of neutron stars. When two of these ultra-dense remnants of massive stars spiral toward each other, the energy released at the moment of impact could explain the immense power of short gamma-ray bursts. Another possible source lies in the collapse of massive stars into black holes, a process known as a hypernova, which may drive long gamma-ray bursts by ejecting colossal jets of energy at nearly the speed of light. What makes gamma-ray bursts even more astonishing is their unpredictability. They occur without warning, often in distant galaxies, and last only a few seconds to a few minutes, making them incredibly difficult to study. Yet, these fleeting events leave behind clues, such as afterglows in other wavelengths of light, that astronomers can analyze to piece together their elusive origins. Advanced observatories equipped with gamma-ray detectors are constantly scanning the skies, hoping to catch these rare events in action. Beyond their enigmatic nature, gamma-ray bursts hold profound implications for the universe. Their powerful radiation can impact the environments around them, potentially influencing star formation or even playing a role in the evolution of life by altering planetary atmospheres across vast distances. As we continue to explore these cosmic phenomena, gamma-ray bursts challenge our understanding of the forces shaping the universe. They remind us of the immense power locked within celestial events and the untapped mysteries still waiting to be uncovered. Leaving behind these explosive marvels, we now turn to another ripple in the cosmic fabric, the mysterious gravitational waves that offer a new way of observing the universe. Now turning to the mysterious ripples that traverse the very fabric of the universe, gravitational waves have transformed how we observe and understand cosmic events. These faint distortions in space-time are caused by some of the most massive and energetic occurrences in the cosmos. Imagine two black holes spiraling closer and closer until they finally collide, releasing an immense burst of energy that creates ripples spreading outward across the universe. These ripples, or gravitational waves, were first directly observed just a few years ago, marking one of the most groundbreaking discoveries in modern astrophysics. Even within the Milky Way, the detection of such waves has provided extraordinary insights into events that would otherwise remain hidden. Gravitational waves open an entirely new window for exploring the universe. Rather than depending solely on light, which can be blocked or obscured by cosmic dust and debris, these waves allow scientists to detect phenomena that were previously invisible. For example, black hole mergers, neutron-star collisions, and even events tied to the formation of the universe itself can now be studied in exquisite detail. Each detection brings with it a treasure trove of information about the properties of these objects, their mass, their speed, and even their distance from Earth. One particularly fascinating example is the merging of two neutron stars. Such an event not only creates gravitational waves, but also leads to the formation of heavy elements like gold and platinum, scattering them across the universe. In detecting these waves, we are not just observing the collision, we are witnessing the very processes that forge the building blocks of planets, moons, and even life itself. The technology behind gravitational wave detection is as impressive as the phenomena itself. Advanced observatories like the Laser Interferometer Gravitational Wave Observatory use incredibly sensitive instruments to measure minuscule distortions in spacetime. These distortions are so small they are measured in fractions of the width of an atom, yet they carry information about events billions of years ago and billions of miles away. As we continue to monitor and analyze these cosmic ripples, gravitational waves are reshaping our understanding of the universe, allowing us to see it in a way never before possible. They remind us of the interconnectedness of all things and offer profound insights into the violent and creative forces that mold galaxies, stars, and even the elements we find here on Earth. With gravitational waves expanding the boundaries of what we know, let us now turn to another cosmic conundrum, the puzzling scarcity of lithium in the Milky Way, a mystery that challenges our understanding of stellar chemistry. Moving forward, we arrive at an enigma that has perplexed scientists for decades, the curious case of lithium. This lightweight element, one of the first to form in the universe after the Big Bang, has been found in quantities that simply do not align with predictions. Based on our models of stellar nucleosynthesis, the process by which stars create elements, we should be observing far more lithium in the Milky Way than we actually find. So, where has it all gone? This discrepancy, often referred to as the lithium problem, presents a significant challenge to our understanding of how the universe works at its most fundamental level. To put this into perspective, the theories of cosmic evolution predict specific amounts of lithium should have been produced by the Big Bang, forming a benchmark for what we expect to see. However, when astronomers measure the lithium content in stars, especially older ones, they consistently find levels far lower than anticipated. In fact, measurements indicate only about 1/3 of the lithium that should exist can be accounted for. This shortfall not only defies expectations but also raises crucial questions about the processes occurring within stars and galaxies. One possible explanation lies in the intricate life cycles of stars. As stars age and go through nuclear fusion, they can destroy lithium in their interiors, reducing its abundance. However, this theory cannot fully explain the observed deficit, especially in older, low-mass stars where lithium was expected to be preserved. Another avenue explores whether lithium might be hiding in ways we are not yet able to detect, perhaps locked away in planets, stellar remnants, or even unique cosmic environments we have yet to uncover. Interestingly, the lithium problem forces scientists to reconsider some of the most well-established ideas in astrophysics. If our models of nucleosynthesis are incomplete, it could mean that other fundamental processes within stars or the early universe remain misunderstood. This mystery even invites more speculative explanations, from unknown physical processes operating in the early universe to interactions involving dark matter, the elusive substance that dominates the cosmos yet remains invisible to our instruments. As efforts to solve this conundrum continue, the lithium problem serves as a humbling reminder of the gaps in our cosmic knowledge. It highlights the complexity of stellar chemistry and underscores the need for continued exploration as we refine our models of the universe. With so much still to uncover, let us now journey to another intriguing feature of the Milky Way, the shadowy zone of avoidance and its secrets hidden from our view. With the next phase of the journey in sight, we turn to a region ominously named the Zone of Avoidance. This part of the Milky Way, veiled in a dense curtain of interstellar stars, gas, and dust, has eluded our understanding for decades. Located along the plane of our galaxy, the Zone of Avoidance is not so much a single location, but rather an entire swath of the sky where visibility becomes virtually impossible. Imagine trying to peer through fog so thick that even the most powerful telescopes struggle to see through it. That is precisely the challenge astronomers face when attempting to study this region. The core issue lies in the sheer density of material concentrated along the galactic plane. Stars, gas clouds, and cosmic dust form such a thick barrier that they obscure up to 20% of the observable sky, blocking our view of the galaxies, structures, and phenomena that lie beyond. This phenomenon acts almost like a cosmic blindfold, preventing us from constructing a complete map of the Milky Way and the universe beyond. Even infrared and radio wavelengths, which can typically see through dust clouds, face significant limitations in fully penetrating this dense region. But the zone's mysteries do not stop there. Researchers suspect this hidden area could hold crucial clues about the Milky Way's overall structure, as well as large-scale cosmic features like the Great Attractor, a gravitational anomaly influencing the motions of entire clusters of galaxies. Without a clear view of the Zone of Avoidance, it remains difficult, if not impossible, to confirm the presence of such structures or understand their impact on our galaxy. Recent advances in observational technology, however, offer a glimmer of hope. Instruments sensitive to other wavelengths, such as radio telescopes and space-based observatories, are gradually peeling back layers of the zone's veil. For instance, in recent years, astronomers have started to uncover previously hidden galaxies lurking behind this shroud. Every discovery made in this enigmatic zone deepens our appreciation for the galaxy's complexity and provides a step forward in piecing together the Milky Way's full story. The Zone of Avoidance serves as a stark reminder of how much remains hidden, even within our own cosmic backyard. It challenges us to innovate and expand the boundaries of exploration, proving that even in an era of incredible technological advancement, there are still vast regions of the universe where the unknown reigns supreme. As we persist in unraveling the secrets of this cosmic blind spot, let us now turn to another fascinating mystery that roams the Milky Way, the rogue planets, the wanderers drifting through the void without a home. Now turning to the enigmatic heart of our galaxy, we arrive at Sagittarius A, a supermassive black hole sitting roughly 26,000 light-years away in the direction of the Sagittarius constellation. While its existence has been known for decades, Sagittarius A continues to puzzle astronomers with its erratic flares and complex behavior. These flares, sudden bursts of high-energy radiation, often seem to erupt without warning, shining up to 100 times brighter than normal before fading away within hours. What triggers these outbursts remains one of the greatest unanswered questions about Sagittarius A star. Some theories propose that these flares arise from material falling into the black hole's gravitational grasp, briefly heating up as it spirals inward at near light speeds. Others suggest magnetic reconnections akin to solar flares on the Sun may be responsible for these explosive events, but the mysteries surrounding Sagittarius A star go far beyond its flaring episodes. It plays a colossal role in shaping the Milky Way, exerting its immense gravitational influence over countless stars, gas clouds, and even entire star clusters orbiting its vicinity. This gravitational force helps maintain the structure and stability of the galactic core, making Sagittarius A star an anchor of sorts for the entire galaxy. Scientists have even speculated that its presence could be critical to the ongoing formation and dynamic evolution of the Milky Way itself. However, one of the most perplexing aspects of this cosmic giant remains its accretion disk, or rather, the lack thereof. Most supermassive black holes are surrounded by a vast accretion disk, a swirling mass of gas, dust, and other material being drawn toward the event horizon. Yet, Sagittarius A star appears strangely dim, with very little detectable material actively feeding into it. This has led researchers to question whether the black hole is currently in a dormant phase or if some unknown process is preventing material from accumulating. Adding to the intrigue, recent observations suggest there may be faint ejections of matter flowing outward from Sagittarius A star, hinting at the possibility of weak, intermittent jets. These jets, if confirmed, could provide invaluable clues about how black holes interact with their surroundings and influence their host galaxies over cosmic timescales. Each new observation of Sagittarius A star brings us closer to understanding its complex nature, while reminding us how much there is still to learn about these cosmic enigmas. With the mysteries of Sagittarius A star sparking our imagination, let us now shift our focus to the celestial wanderers that defy convention rogue planets, the loners drifting endlessly through the Milky Way without a star to call home. With the next phase of the journey in sight, we return to the fascinating enigma of the Fermi Bubbles, those colossal gamma-ray, emitting structures stretching tens of thousands of light years above and below the Milky Way center. These massive bubbles, discovered over a decade ago, continue to perplex scientists with their sheer size and energy. But what makes them even more intriguing is how their energy is distributed across their vast expanse. Recent studies suggest that the gamma rays within the Fermi bubbles are not uniform but instead vary in intensity, hinting at a complex origin story that we are only beginning to piece together. Some researchers believe these variations could point to a turbulent past event at the galactic core, possibly involving a powerful burst of star formation or a sudden feeding frenzy by Sagittarius A star, our galaxy's supermassive black hole. Digging deeper, the interaction of the Fermi bubbles with the Milky Way itself adds another layer to this enigma. These structures appear to be interacting with the galaxy's halo, a vast region of hot gas surrounding the Milky Way. This interaction likely generates shock waves that continue to shape the structure and dynamics of the halo, offering scientists a rare glimpse into the processes that govern galactic evolution. These shock waves may also provide critical insights into the elusive phenomenon of galactic winds, powerful streams of energy and particles that can drive material out of a galaxy, influencing its ability to form new stars. By studying these interactions, researchers hope to unravel the role the Fermi bubbles play in regulating the Milky Way's star-making potential. Adding to the intrigue, observations have revealed that the edges of the Fermi bubbles glow with a peculiar brightness, suggesting they might be sites of high-energy particle acceleration. This acceleration could be linked to cosmic rays, those mysterious charged particles that zip through space at nearly the speed of light. If true, the Fermi Bubbles could be a key player in understanding where cosmic rays originate and how they spread throughout the galaxy. Each new discovery about the Fermi Bubbles opens a window into the Milky Way's hidden past, painting a picture of a galaxy shaped by explosive events and ongoing interactions. As we uncover more about these galactic echoes, we come closer to understanding the forces that have sculpted our galaxy over billions of years. And while the Fermi Bubbles remind us of the intense activity that can occur in the heart of the Milky Way, they also prompt a deeper question about the quieter yet no less mysterious outskirts, the rogue planets we mentioned earlier, unbound and free-floating through the galaxy's vast expanses. Let us now journey to these solitary wanderers and the secrets they hold. Now turning to the elusive mystery of the dark matter halo, we dive deep into one of the most perplexing enigmas in astrophysics. Surrounding the Milky Way like a vast, invisible cocoon, the dark matter halo is thought to account for a staggering portion of the galaxy's mass. Yet, despite its immense influence on the motion of stars and galaxies, dark matter itself remains undetectable by conventional telescopes. This invisible substance neither emits nor absorbs light, leaving scientists to rely on its gravitational effects to infer its existence. The way stars at the outer edges of the Milky Way move far too quickly for the visible matter to account for provides compelling evidence of this unseen force. Recent efforts to uncover the nature of dark matter have brought cutting-edge experiments like the LUX Zeppelin project into the spotlight. Located deep underground to shield it from interference, this state-of-the-art experiment aims to detect incredibly rare interactions between dark matter particles and ordinary matter. By using a massive tank filled with liquid xenon, scientists hope to catch fleeting signs of these mysterious particles, often referred to as weakly interacting massive particles. While no direct detections have been made yet, each attempt refines our understanding and narrows down the possibilities of what dark matter could be. Adding another layer to the mystery, alternative theories are being explored that could challenge our fundamental understanding of the cosmos. Some researchers speculate that dark matter might not be made of particles at all, but could stem from undiscovered forces of nature or even extra dimensions. The very idea that the dark matter halo might hold clues to phenomena beyond our current scientific framework is both thrilling and humbling. As we delve deeper into this invisible realm, the potential discoveries extend far beyond the Milky Way itself. Unlocking the secrets of the dark matter halo could transform our understanding of how galaxies form, evolve, and interact on a cosmic scale. It could even lead to breakthroughs in physics that redefine the laws governing the universe. And while this invisible universe challenges our ability to comprehend it, it also reminds us of the boundless curiosity that drives human exploration. Just as the dark matter halo envelopes the Milky Way, shaping its structure and destiny, it also serves as a powerful symbol of the mysteries that remain just out of reach, waiting to be uncovered. With this, we now turn our attention to another puzzle lurking in the vastness of our galaxy, one that takes the form of renegade stars hurtling through space at unimaginable speeds. With the next phase of the journey in sight, let us explore the breathtaking future of our Milky Way as it faces an inevitable cosmic collision with the Andromeda galaxy. This monumental event is predicted to take place around 4 billion years from now, and while that might seem like an eternity to us in astronomical terms, it is just around the corner. The Milky Way and Andromeda are currently hurtling toward each other at an astonishing speed of over 70 miles per second, drawn together by their mutual gravitational pull. The sheer scale of this encounter is almost beyond comprehension, as each galaxy contains hundreds of billions of stars, along with planets, gas clouds, and dark matter halos. At first glance, such a collision might sound catastrophic, but the reality is surprisingly complex. When these two colossal galaxies meet, their initial encounter will trigger dramatic tidal forces, stretching and distorting their shapes like cosmic taffy. Over the span of billions of years, they will engage in a celestial dance, orbiting and merging repeatedly until they settle into a unified structure, often referred to as Milkomda. Despite the apparent violence of this process, the vast distances between stars mean that direct collisions between individual stars are incredibly rare. Instead, the mingling of gas and dust will spark a spectacular burst of star formation, lighting up the merged galaxy with new, brilliant stars. This transformation will also reshape the night sky as seen from any surviving planets, offering a breathtaking view of galactic streams and vast stellar nurseries. However, this merger will not only influence the structure of the new galaxy, but also its future dynamics. For instance, the supermassive black holes at the centers of the Milky Way and Andromeda are expected to eventually merge as well, creating a single, even more massive black hole that will dominate the core of Milkomda. Interestingly, this collision is part of a much larger story of cosmic evolution. The universe is constantly changing, and these galactic mergers play an essential role in shaping its structure over billions of years. For our Milky Way, this fusion with Andromeda will mark a transformative chapter, altering its form and paving the way for new astronomical phenomena to emerge. While the thought of such a dramatic event might evoke a sense of unease, it also serves as a humbling reminder of our galaxy's place within the vast tapestry of the cosmos. As we conclude our exploration of the Milky Way's mysteries, from its dark matter halo to its future collision with Andromeda, we are left with a profound sense of wonder about the forces that shape our universe. These phenomena remind us that the cosmos is still full of unknowns, waiting to be discovered by curious minds. If any of these mysteries captured your imagination, feel free to share your thoughts in the comments below. And if you enjoyed this journey through the Milky Way's enigmas, make sure to like this video, subscribe to our channel, and turn on notifications so you do not miss out on our next adventure into the universe's greatest mysteries. Thank you for joining us, and until next time, keep looking up at the stars. Now turning to the conclusion of our journey through the 25 most mysterious phenomena in the Milky Way, we find ourselves marveling at the sheer complexity and wonder of our galaxy. From the elusive dark matter halo that holds the Milky Way together, to the enigmatic fast radio bursts that flash like cosmic signals, to the breathtaking future collision with Andromeda that will reshape everything we know about our galactic home, the mysteries of the Milky Way are endless. Each phenomenon we explored offers a glimpse into the intricate dance of matter, energy, and forces that govern the universe. These mysteries remind us not only of how much we have discovered, but also of how much more remains to be uncovered. The Milky Way is far more than just a collection of stars and planets. It is a dynamic, ever-evolving masterpiece filled with secrets that challenge our understanding while igniting our curiosity. As we continue to observe, explore, and question the cosmos, we take small but significant steps toward unraveling the story of our galaxy and ultimately our place within it. What mystery from this journey captivated you the most? Was it the fascinating zombie stars that cheat death, the immense Fermi Bubbles glowing in gamma rays, or the rogue planets wandering the galaxy alone? Let us know your thoughts in the comments below. We would love to hear which of these cosmic enigmas inspired you the most. If this adventure through the wonders of the Milky Way left you in awe, be sure to like this video, subscribe to our channel, and turn on notifications so you will not miss our next deep dive into the mysteries of the universe. Thank you for being a part of this exploration, and until next time, keep looking up at the stars. The answers to the greatest questions of existence might just be waiting to reveal themselves.